Okay, let's look at some molarity and dilutions. I'm beginning here with one of these. All right, so suppose you have this many grams of gaseous HCl and you want to dissolve it in enough water to make this solution. What concentration would it be? So this many grams divided into this. Keep in mind molarity is moles per liter. So we're going to convert this to moles, and then we're going to convert this to liters. We'll take this divided by this, and it will give our answer. So let's start with 2.94 grams of HCl, and we're going to convert it to moles. So in order to do that, you need the molar mass of HCl. So hydrogen, according to the periodic table, is 1.008 grams per mole, plus chlorine is 35.45 grams per mole. There's 1.008 for hydrogen and 35.45 for chlorine. So we add that together, and that comes out to a total molar mass of 1.008 plus 35.45 is this. We round to the hundredths place. That is 36.46 grams per mole HCl. Okay. So here's how we actually go about using this then. So we're going to want to put grams of HCl on bottom. That way it can cancel with this. And we're going to convert from grams to moles. Remember, so that's the goal, right? So we're going to put moles of HCl on top. And what that's going to do is we're going to put the molar mass here, and that's going to allow us to go from grams to moles. So we have 1 mole has a mass of 36.46 grams for HCl. So this is saying take this divided by this, and we'll get an answer in moles. So 2.94 divided by 36.46 equals 0.080636. That's way more than enough significant figures than we're going to need in the final answer. I'll add another one just for good measure. So there's our moles of HCl. Now let's turn this into liters. So we've got 26.8 milliliters times milliliters on bottom, liters on top because they're trying to get liters. And then 1 liter is 1,000 milliliters, because remember, milli means 1,000, and you put the big number next to the small unit. So if you do that, then 26.8 divided by 1,000 equals 0.0268 liters. So there's our moles, there's our liters. So we're going to take 0.0806363 moles of HCl divided by 0.0268 liters of HCl. And what is that going to give us? 0.0806363 divided by 0.0268. It's going to give us that. 3.008817 blah 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 moles per liter HCl. Now we're going to have 3 sig figs here, 3 sig figs here. All of our calculations are based on this, plus the molar mass with 4 sig figs. So we're going to run to 3 sig figs on account of these numbers here. So we're going to call that 3.01 molar, or you could write it out moles per liter, whichever suits your fancy, HCl. Now, having done that, I'm going to show you an alternative solution that you might find a little less messy, and that is also equally valid with this. So what's an alternative way I could have calculated that the concentration is 3.01 molar HCl? I could have said, look, molarity of moles per liter, I'm going to convert this to moles, I'm going to convert this to liters. So essentially, we took this, did some conversion, and divided it by the result of this going through a conversion. So it's converted version of this divided by converted version of this. I can take advantage of that. I could start with 2.94 grams of HCl divided by 26.8 milliliters of HCl solution. So I would need to do some conversion, of course, with this. Now, what could I do? I still would need to show the work for molar masses. I'm still going to need that. Just like we did like miles an hour to kilometers a second or whatever, you can do a multi-factor conversion here. So I'm going to convert the top part first. I'm going to put the molar mass here of grams of HCl to moles of HCl. And then 1 mole has mass of 36.46 grams. So, okay. That being what that is, you can then notice that we'll have gram cancel gram to have where now it's moles per milliliter. Cool. Let's continue our conversion. We want milliliters to cancel, so I'm going to put milliliters HCl on top and then liters of HCl on bottom because we're going to convert from milliliters to liters. I'm just putting this for keeping things straight, and you'll notice that if we run all this through, gram cancel gram and milliliter cancel milliliter, we're going to end up with moles per liter, which is molarity. So anyway, 1 liter is 1,000 milliliters. So if we go through and do this, check out what we can do. 2.94 divided by 26.8 equals, divided by 36.46 equals, times 1,000 equals the exact same result from before. 3.0088176778 moles per liter, aka molarity, HCl. We'll round that to 3.01 moles per liter, HCl, or you could just write a capital M instead of moles per liter if you so prefer. But it's two different ways of arriving at the same answer, taking advantage of the fact that we're just taking converted version of this divided by a converted version of this. So regardless of whether you follow the format in the notes or try it out this way, either way is completely fine for that. So having mentioned that, let's continue onward. You'll find the same process applies here too. Do note that this is kilograms. So just like we had to convert this to liters before we could use it, you better convert this to grams before you can use it. So regardless of whether you do two separate calculations and then divide one by the other, or whether you do it all at once, make sure you involve in there a conversion of this from kilograms to grams, or this won't work for you. All right, now onward. Give the concentration of all ions in that solution concentration of sodium carbonate. So here's how we're going to do it. There's sodium and carbonate. Yes, you have to recognize CO3 as a polyatomic ion. So here's how we're going to do it. 0.0050 molarity Na2CO3 times. Notice, let's do the sodium first, then I'll do the carbonate. Do you notice that there's 2 sodiums for every molecule? Here's how we're going to phrase that. For every 1 mole of, let's see, what is it? Na2CO3. So for every 1 mole of Na2CO3, there's 2 moles of sodium. By the way, this is moles per liter, and this is this many moles of this divided by 1 liter of this. So the moles of this will cancel moles of this. So technically it actually does work out correctly. And I'll put sodium plus to remind it's an ion. But anyway, this is a way of showing that you have 2 sodiums in every molecule. So anyway, when you do that, essentially you're just taking this times 2, and which should be 0.01, but to prove it, 0.005 times 2 is 0.01. Now you'll notice this is 2 significant figures. Make sure you got 2 significant figures here. 0.010 molarity sodium ion. You could also write moles per liter instead of capital M, whichever is fine for you. And since that's small, we need to change that to scientific notation. That's 1.0 times 10 to the minus 2 molarity sodium plus ion. Just to prove that, you convert that to scientific notation. Look, it's 1 times 10 to the negative second. Let's do the same thing for the other ion. So Na2CO3 times, let's do carbonate ions. So for every 1 mole of Na2CO3, this is 1 carbonate, because carbonate is CO3. So there's only 1 carbonate per molecule. So we're at 1 mole CO3 2 minus, because that's carbonate. So in other words, we just wind up with the same number again, because this times 1 divided by 1. So it's 0.0050 molarity carbonate. And we got to change that to scientific notation, so that's 5.0 times 10 to the 1, 2, 3, negative third molarity carbonate. Alright, that's the process you go through, this sort of conversion factor. You're going to follow the same pattern down here. Okay. Onward then. Let's look at how many grams of a chemical do you need to make a particular concentration. Alright, so here's the thing, ladies and gentlemen. There's a couple of ways you could potentially go about doing this, and I'll show you one of the notes, and I'll show you another particular way you potentially do it also. Okay, so here's how we looked at it, particularly following the format of the notes. So 2.5 liters, 12.3 molar solution. So here's the thing. Molarity is moles per liter. So if we take liters times moles per liter, liter cancels liter to just give moles. Look, liter times mole per liter cancels to give moles. And then you can use the molar mass to take your number of moles and convert to grams by using the molar mass. So that's our strategy. 2.5 liters of this formaldehyde, it's easy to just write the formula HCHO, times, and then 12.3 moles of HCHO for every 1 liter of HCHO, keeping those chemical identities and everything, breaking molarity down into moles per liter so that we can cancel units. Okay, look, liter cancels liter, give moles, and then what do we have here? We have 2.5 times 12.3 equals 30.75 moles. Of HCHO, and then what's the molar mass of that so that we can turn that into grams? Well, H is, there's 2 hydrogens. Hydrogen is 1.008, times that by 2, plus carbon, which is 12.01, plus oxygen, which is 16.00. And what does that add up to? So 2 times 1.008 plus 12.01 plus 16 is that. And we round to the nearest hundredth, so that is 30.03 grams per mole HCHO. So we're going to have this many moles was the result of this right here, because again we got 2.5 times 12.3. So cool. And then we're going to times that by something in order to make this work. What are we going to have to do? We're going to have to put moles on the bottom in order for it to cancel. We want grams in order to get grams in our unit. Sorry, for our answer. So what does it see? HCHO, HCHO. So the molar mass is that many grams per mole. So the weight of 1 mole is 30.03 grams. So in other words, we're going to take this times 30.03. And that's going to equal 923.4225 grams of HCHO, which we then round to 4 sig figs, 3 sig figs, 2 sig figs. Oh, better do 2 sig figs. 920 grams of HCHO. Little side note, this is one of the things I was going to mention earlier. Let me fold this to get this out of the way from a previous example I did. You could do that slightly differently, because why not 2.5 liters HCHO times 12.3 mole HCHO, 1 liter HCHO. If we're going to use the grams per mole, why not just keep this equation going and do it all in one step without writing down this intermediate answer? You could say mole HCHO, grams HCHO, because you put mole down here because mole's up here, and then grams because that's what you need, and it turns out this is the molar mass. So 1 mole is 30.03 grams of HCHO. So you're going to get the exact same answer of 923.4225 grams of HCHO, rounding to 920 grams of HCHO, equally just the same. Thirdly, a little thing I'll mention, you could treat this like an algebra equation also, where molarity equals moles per liter. And so then you could just times liters to both sides. So liters times molarity equals moles. And then you take the liters times the molarity, which is what we did here. There's liters, there's molarity, in order to get moles. And then you times the grams per mole in order to get units of gram. So that's another potential alternative way of considering, of just ways that you could have known to have done this in the first place. Either way, regardless of whether you break it up into small steps where you do this, write an intermediate answer, do another step, and then write your final answer, or if we just do it all in one piece, either is equally fine in terms of the test, because look, they yield the same answer. Okay, so having said that, let's move on. Looking at these other ones, notice booby traps lay ahead for you. That's milliliters. And this is milligrams. So if you want to do molarity, remember that's moles per liter. And in order to get from moles to milligrams, you got moles. You're going to be using the molar mass to turn moles into grams. So when you convert, this will give you grams for the moles part up here, and they're going to need to convert grams to milligrams. Milliliters, likewise, you can't do anything with this calculation until you convert milliliters to liters first. So you're going to need to make sure to convert this to liters, and then do your math to get your things out of here, find out how many moles, and then take the moles, convert to grams, and then take the grams and convert to milligrams, and that will give you the answer for this. Alright, now, let's go onward to dealing with these ones right here. This is the dilution calculation. So you're either watering it up or asking how many milliliters of something do you need. So if you are diluting something or asking how much do you need to prepare of something or whatever, there is a couple ways to solve this, and I'm going to go through what most people tend to prefer from year to year, which is the version where you memorize an equation and you use it. More specifically, you can use the equation M1V1 equals M2V2. Now, how do you know you can use that? It's because, unlike other ones, there's two different concentrations here. You'll either get two different concentrations or two different volumes. Look at the previous questions. They don't mention any more than one concentration or one volume. There's only one concentration or one volume here. Here, there's only one concentration, one volume. One concentration, one volume. So if you see two volumes, as in maybe further down, like here, there's two volumes, or here there's two concentrations or two concentrations. If you see two of anything, you can use this. All right, as long as it's two of the same thing, as in like, okay, I should say two concentrations, but two concentrations of the same chemical identity. Here we have two concentrations of the same chemical identity, and this is two different volumes, but of the same chemical identity. So that's why you can use this only when it's two of the same chemical identity. If it's different chemical identities, you got to do some stoichiometry. So we need to understand this is starting molarity, starting volume, ending molarity, ending volume. So what volume of this must be used to prepare this? When you see the word prepare and you use it to talk about this, this means this is your volume 2, because it's what you end up with. Whatever you prepare, this is your molarity 2, is what you end up with. What you start with would be your molarity 1. This is your starting concentration. So this is molarity 1, this is molarity 2. This is volume 2 because this is what we end up with. So we need to find volume 1. So I'm going to divide by molarity 1 on both sides, and I'm going to get volume 1 equals molarity 2, volume 2 over molarity 1. Now the beautiful thing is, as long as, in this case we have two molarities, as long as they're the same units, and they are moles per liter, then you don't need to worry about converting this to liters, because here's the thing. If you put molarity and molarity, they're going to cancel. So if you plug milliliters in, you'll get milliliters out. You plug liters in, you get liters out. You plug deciliters in, you get deciliters out, etc. So if we put milliliters in, you're going to get milliliters out. Hooray. So let's plug in the numbers. So M2 is 0.25 molar times the volume oops, I wrote the wrong thing. Let me get the white out. 75.0 milliliters HCl. So that's our molarity 2, our volume 2. What's our molarity 1? It's 12 molar HCl. You could break this down into moles per liter if you like, but it's going to give the same result either way. Remember, capital M is the same as moles per liter. So molarity of HCl cancels molarity of HCl, leaving milliliters of HCl as your answer, and indeed, it should have milliliters of HCl as the answer's unit, because look what it asked for. Okay, so what is this saying? 0.25 times 75 equals, divided by 12 equals 1.5625, and what was it again? Milliliters HCl. So more specifically, rounding is a good thing here. 2 sig figs, 3 sig figs, 2 sig figs. So let's round to 2 sig figs. So that's 1.5 milliliters. And more specifically, this is the volume of 12 molar HCl that we need to use in order to get this. So in other words, if we use this many milliliters of this much solution, and if we take this and add enough water to that, it goes from this many milliliters to this many milliliters. So we water it up from 1.5 to 75. Its concentration will become less. That should make sense. If you add water, the concentration becomes less. And so the concentration becomes only 0.25 once you add all that water and make it have that much extra volume. Okay. So that's how you go about doing that one. This is going to be the same sort of idea. You're going to identify your molarity 1, molarity 2, volume 1, volume 2. Notice how you're given liters and asked for liters. So that's nice. All right. So here, instead of molarity, here we have two molarities and you're solving for volume. Here we have two volumes and you're solving for molarity. And notice the other complication. Your volumes have different units. Oh, that's meant to be a trick. So you need to make sure to convert them to the same unit. So for no particular reason, it actually doesn't matter which one we do, because here's the thing. We're going to be rearranging the equation, plugging in these numbers, and getting the units. And it doesn't actually matter whether you use milliliters or liters as your volume, and here's the reason why. I'm going to show you with the equation. So let's identify M1, M2, V1, V2. So it says this volume of this concentration is diluted to that. So when you dilute it to this means like this is your final result. And since this is a volume, this is volume 2. What is the concentration of the new solution? This means your ending solution that you get at the end. So this is your M2. So this is volume, so this is V1, and this is molarity at the beginning, so it's molarity 1. So M1V1 equals M2V2. Let's rearrange that. What are we looking for? We're looking for the new concentration, so we need to get M2 by itself. So divide by V2, divide by V2. So M1V1 over V2 equals M2. This will give the new concentration. Now notice something, volume 1 divided by volume 2 just cancels out. So if you have milliliters divided by milliliters, it's just going to cancel to leave molarity. If you have liters divided by liters, it will cancel to leave molarity. So I'll convert this to liters just because. You could convert this to milliliters, you'll get the same thing. You get the same answer in the end. 75.0 milliliters times milliliters on bottom, liters on top, and 1 liter is 1,000 milliliters. So what do we get? 75 divided by 1,000 is 0.0750 liters. Making sure we keep the same number of sig figs. 75.03 sig figs. This is still 3 sig figs. Okay. So we then take this and plug it in down here. So what's M1? It's this, 12.5 molar times what's V1? This one. But careful. Make sure you're using the same unit as the other volume. So 0.0750 liters. Oops, I almost forgot HCl. HCl. Oops, I actually am totally not even paying attention, so let me back up a sec. Adding in our chemical identities. H3PO4 is the formula of phosphoric acid. So that's molarity phosphoric acid times 0.0750 liters H3PO4. And then we divide that by volume 2, which is this, 5.00 liters H3PO4. And then when we do that, what do we get? 12.5 times 0.0750 equals that much so far. And then divided by 5, and we're going to get this, 0.1875. What are our units? Well, liters cancel liters to give molarity H3PO4. Now that's not rounded right yet. 3 sig figs, 3 sig figs, 3 sig figs. So all numbers given at 3 sig figs. So, and that's infinite sig figs, by the way. So let's round that to 3 sig figs. 0.188 molarity phosphoric acid. You could also write moles per liter instead of capital M. That would be equally acceptable. Alright, so that's how that goes. Always watch to make sure that you're dealing with equal units and not have like milliliters and liters or something like that. Alright, well that takes care of how to